So we will talk on a new topic, and the topic will be NMR, that's nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance, or simply NMR, is a very important and useful technique that is used in fields like chemistry and medicine, and this technique comes from nuclear physics. So what is NMR and why is NMR important? There are two uses of whole spectroscopy. First, with the help of spectroscopy, you can find out the amount of a substance, how much of something is present. Second, you can find out the structure of an unknown compound. NMR is mostly used to predict that, if any atom is present, then how many different forms an atom can exist in different environments. Before understanding NMR, it is necessary to understand atom because the first word comes in NMR, which we call nuclear, that is, it will deal with nucleus somewhere. And if we want to understand nucleus, then we will try to understand the structure of the atom. If I draw the structure of an atom, then this is my atom and there is a nucleus somewhere in the middle. This nucleus is made of two things, that is proton and neutron. Proton has positive charge and neutron is neutral. Due to this proton, there is a positive charge on the nucleus. Apart from this, we know that there are electrons here and these electrons have negative charges. When the discovery of electrons started, then one thing was understood, that the electron not only revolves around the nucleus, but it also spins at its own place. So this our electron will not only revolve around the nucleus, it will also revolve around its place. One possibility is it may revolve counterclockwise, the other possibility is it may revolve clockwise. So we've got two electrons here, the electron has negative charge. We have read in physics about rotational motion that every rotating body has got something called as angular momentum. When these electrons will spin, then these electrons will have some angular momentum. Its angular momentum is written as under root of small s into small s plus 1h upon 2 pi. Remember that angular momentum is a vector quantity. It depends not only on the magnitude but also on the direction. Here the small s will be called the spin quantum number. In case of electron, the value of s is fixed. Its value is half. The magnitude is known by angular momentum, but the direction in which our electron is moving is known by magnetic quantum number. Here we are denoting the magnetic quantum number by ms, it will be plus half or minus half. We have seen the basic information about electron. After this, in 1924, Pauli predicted that the way the electron rotates in its place, in the same way our nucleus will also rotate in its place. So now we come to the nucleus. The nucleus is made up of protons and neutrons. The nucleus also spins in its place either in clockwise direction or in anti-clockwise direction. Here, the angular momentum of nucleus is written by under root of I into I plus 1h upon 2 pi. In the case of nucleus, spin quantum number is not fixed because every atom has got different number of proton and neutron. So, I can say that this composition of a nucleus is different in every atom. Remember this distinction here. In the case of an electron, the value of s remains constant, and in the case of the nucleus, the value of I varies. We shall denote the magnetic quantum number of the nucleus by Mi. Now we have understood that we have electron and nucleus and both spin in their respective places. There is a topic related to current and magnetism, which we call the magnetic effect of electric current. To understand this, we will take a paper and take a wire in that paper. I round this wire like this. We can call it loop. Now we will connect this wire to the positive and negative battery. When I switch on, current will start flowing through it. The flow of current starts from positive and goes towards negative. Therefore, I would say that current means motion or movement of charge. There are two types of charge: positive charge and negative charge. If the negative charge, that is electron, will move, then the flow of current will start from negative and go towards positive. Similarly, if the positive charge, that is nucleus or proton, will move, then the flow of current will start from positive and go towards negative. You have a magnet that will have a north pole and a south pole. The magnetic field of the line starts from north and goes towards south. This is the basic principle of magnetism. If current is flowing in this wire, then a magnetic field must also be generated around this wire, because moving current or charge will always generate magnetic field. To interpret its north and south pole, I got right and thumb rule. The right and thumb rule states that if you place your finger in the direction of current in the wire, your thumb will always point toward the north pole. If I apply this rule here, then north pole will come towards the top and south pole towards the bottom. It is not necessary that there should be displacement of charge. Even if it is spinning while standing at its place, it will produce magnetic field around itself. If this electron spins counterclockwise, my thumb will point to the south pole. Now my electron will behave like a tiny magnet. Similarly, if the electron spins clockwise, there will be bottom south pole and upper north pole. If the nucleus spins counterclockwise, then with a positive charge, the thumb points toward the upper north pole. And if it spins clockwise, then the bottom will be the north pole, and the top will be the south pole. So till here I am understanding two things: that if my nucleus spins, then it acts like a tiny magnet, and if electron spins, then it also acts like a tiny magnet. And the electron does not just spins, it also revolves. I have nothing to do with electron. I am more focused on the nucleus. Nucleus is acting like a magnet, and in the name of nuclear magnetic resonance spectroscopy, there is nucleus as well as magnet. Now only resonance is to be understood. So now in the next video, we will see what is resonance in NMR? And how is spectroscopy possible when the nucleus has a magnetic field? So let's meet in the next video.